Hello, this is 5.4 part 2. So you hopefully should have watched part 1, and today we are going to finish up our lesson. And started off with this funny diagram that I thought I would just post for you guys. Asymptotes, a danger to our children, and there's a kid sliding down to negative infinity. So I'll start off with a quick review of an important part of part 1 that I did. And this is the sort of the last thing that we touched on in the previous video, which was how to identify horizontal asymptotes, okay? So, in order to do this, your function needs to be in the form P of x over Q of x, okay? It can't be like two fractions added together like that. That doesn't work. So it has to be, I need a bigger eraser. It has to be in this form here, P of x over Q of x. Okay, and there's 3 different types of this form, and they will tell you different things about the horizontal asymptotes. Okay? What you always want to look for when you're identifying whether or not it has a horizontal asymptote and what kind of horizontal asymptote is you always want to look for the leading power. Okay? So let's say, for example, and this will be the first example, that you have f of x equals x cubed plus 2x squared plus 1 over x plus 2. And that's your function that you're dealing with. You always want to look for the leading power. So in this case, my leading power on the numerator is this x cubed right here. Okay, and my leading power in the denominator is this x. These ones, they're not going to matter in comparison with your leading power. And what this tells you is that is whether or not it has a horizontal asymptote. So if you think about this with me, we've got an x to the cubed in our numerator, okay, and this is the graph, okay. So if we got an x to the cubed in the numerator and an x in the denominator, it's basically saying a really big value, right, x to the cubed, divided by a not as big value, the x, okay. This is the case in which we have a bigger power on top and a smaller power on bottom. A bigger number divided by a smaller number is going to have a value that continues to increase. It continues to go up. The y value continues to go up to positive infinity. So that means it's not going to have a horizontal asymptote. It's not going to have a line horizontally that the graph will approach and not touch. It's going to keep going skyward. So in this case, when P of Q is greater, or excuse me, when P of X is greater than Q of X, when P of X, that's your numerator, is greater than Q of X, there is no horizontal asymptote. Okay, that's the first instance. The second instance is, let's say your denominator has a greater power. So let's say you have f of x equals x plus 2 over x cubed minus 3. Remember, you're always looking for the highest power. So on the top, your highest power is going to be this x. And in the denominator, your highest power is going to be this x cubed. Now, in this instance, you have your x in the numerator and your x cubed in the denominator, and so this is saying you've got a smaller figure on top and a much larger figure on bottom. And so as those values go out towards infinity and negative infinity, those x values continue to increase to the infinities. That number, a smaller number divided by a bigger number, is going to get smaller and smaller and smaller and smaller and approach 0. So, in this case, when p of q, that's your numerator, is less than, I keep saying p of q, I mean p of x, sorry. When p of x, that's your numerator, is less than q of x, then your horizontal asymptote is going to be at 0. Is y equals 0. So you're going to have a horizontal asymptote at 0. Okay, third, when they're the same power. So let's say this is the third option. For example, you've got f of x equals, let's go, 2x squared plus whatever, doesn't matter, plus 6 over 3x squared minus 2. Okay? In this case, you always go for your leading powers. You've got this x squared in the numerator and this x squared in the denominator. Think about this. The x values are approaching the infinities, okay? And you've got the same value divided by the same value. So in that case, these greatest powers are going to cancel each other out, and you're going to have a horizontal asymptote at the leading coefficients. So in this case, when p of x is the same power as q of x, your horizontal asymptote, how do they write it up here? Is the leading coefficient of p, is the leading coefficient of p over the leading coefficient of q. So in the case of this example, you would have a horizontal asymptote at y equals 2/3. Okay, that was just some review. Now let's get started on part 2. And by the way, this graph that explains all of this is on page 342. But instead of memorizing just this table, I would encourage you to try and understand why these different cases result in no horizontal asymptote, a horizontal asymptote at 0, or a horizontal asymptote at the leading coefficients divided by the leading coefficient of the denominator. So hopefully you actually understand why that is. Okay. We did this one in the last video, so here we go. Time to do some examples. It wants us to identify the zeros and the asymptotes of each function and then graph. So this one, first thing we're going to do is identify the zeros. So when we're dealing with rational functions, to identify the zeros, you're going to factor the numerator, set both of those factors equal to 0, and solve for x. So we've got x squared plus 2x minus 15, so I need two factors of negative 15 that are going to equal 2, so I'm going to choose a positive 5 and a negative 3, and then I'll put that all over my denominator, x minus 1. And so this is the same thing, just in factored form. This is my formula. So my zeros, I'm going to take the two factors of my numerator, x plus 5, and set that equal to 0, and x minus 3 and set that equal to 0. And for my zeros, I'm going to get negative 5 and positive 3. Okay, now I need to figure out my asymptotes, vertical and horizontal. So I'll do vertical first. To figure out my vertical asymptote, I need to set my denominator equal to 0. So let's go vertical asymptote. We set x minus 1 equal to 0, and I'm going to have a vertical asymptote at x equals positive 1. Okay, and last but not least, and this is the thing that we just talked about a lot on the last slide, is my horizontal asymptotes. Horizontal asymptotes. Okay, so what we need to do is go back to our original equation and figure out the leading power. So on the top I've got an x squared, and on the bottom I've got an x. So I've got a higher value on the top being divided by a lower value, and as my x values approach infinity, it's not going to stop anywhere. It's not going to stop going up or going down. So I'm not going to have a horizontal asymptote. Since I have a higher value divided by a lower value, that's not going to approach 0. It's not going to approach any single number. So my answer is I have none. No horizontal asymptote. Then it wants us to graph. I'm going to do this on my graphing calculator and show you what it looks like. And let's see if we did this right. So we've got x squared plus 2x minus 15 divided by x minus 1. Okay. All right. So first of all, let's see what our zeros are. That's where the graph crosses the x-axis right here and right here. And we said that it's at negative 5 and 3. So as you can see, we got that right. Then it looks like we have a vertical asymptote right here. Vertical asymptote at x equals 1, and we do not have a horizontal asymptote. So it checks out. Good job. Go ahead and pause the video and try these next two by yourself. Give me the zeros, vertical asymptotes, horizontal asymptotes. All right, hopefully you did that. To do this first one, I'm going to rewrite it in factored form. So it looks like I can factor an x out of the denominator. So this is going to be f of x equals x minus 2 over x times x plus 1. Okay. To find my zeros, I set my numerator equal to 0. So my zeros, I'll go ahead and hopefully that makes that more clear. Zeros are going to be add 2 to both sides, so zeros are at x equals 2. Okay, vertical asymptote. We set both the factors of our denominator equal to 0, and this one is going to be x equals 0 and x equals negative 1. And then for my horizontal asymptote, go back to my original equation and look at the leading powers. I've got an x on the top and an x squared on the bottom. So this means as my x values approach the infinities, we've got a smaller value being divided by a much larger value, right? We've got that x divided by x squared. So that means as our x values approach the infinities, our y values are going to approach 0. Okay, you take a number and you divide it by a bigger number, it's going to get smaller and smaller and smaller and approach 0. So we've got a horizontal asymptote at y equals 0. Let's go ahead and graph this, see if we got it right. We've got x minus 2 divided by x squared plus x. Alrighty, let's see what it does. Okay, you can see right off the bat, it's a little harder to see our zeros, but right off the bat we've got a vertical asymptote at x equals -1, and it looks like we've got another one here at x equals 0, and that's what we said, so that's good. And we've got a horizontal asymptote right here at y equals 0. And what did we say for our zeros? That we've got a 0 at x equals 2. So what I can do actually is zoom in on that point and then calculate. Well, I might not even have to, because you can see right there it crosses the x-axis at x equals 2. But what you can do to be sure is hit second calc and then go down to 0 and do left bound. Sorry, I'm looking at this in the screen, so it's all backwards for me. Left bound, enter, right bound, enter, and then guess, and it will tell you you've got a 0 at x equals 2. So awesome job on that one. Okay, last one for this slide. So this one I'm going to start off by factoring the top and the bottom. So looks like I can factor an x out of the top. So that gives us 3x plus 1. And then on the bottom, I've got the difference of two squares. So this is going to factor to x plus 3 times x minus 3. And if you did that one on your own, kudos to you. Good job for recognizing that. So let's find our zeros. We have to set the factors of our numerator equal to 0. So this one is just going to be x equals 0 for that one. And then we set this one equal to 0 and solve for x, and we get -1/3. Okay. So those are our zeros. Then for our vertical asymptotes, we set our denominator factors equal to 0, and we get x equals -3 and +3. And then we got to do our horizontal asymptotes. So let's go back to our original equation and figure out the leading powers. On the top, we've got this x squared. On the bottom, we've got this x squared. So they're going to cancel each other out, and we're left with the coefficients. Right? Let me explain this one more time. As our x values are approaching infinity, we've got a large number, x, some value x squared on the top, divided by x squared, it's same thing. So those are going to cancel each other out. And what's left, as you can see, is this 3 in front. So that's 3 over 1. So we're going to have a horizontal asymptote at y equals 3. Very, very cool. Y equals 3. So let's graph this and see if we did this right. And I've said this before, but if you don't have a graphing calculator at home, there's this cool app on your smartphone called Wabbit. It's like rabbit spelled with a W. Or also on a laptop, there's Desmos calculator. Okay, I didn't zoom out. Bear with me. Here we go. Okay, wait a minute. That does not look right. X squared plus x squared. Oh, you know what? I typed it in wrong. Error on my part. Here we go. Look at that, people. Look at that. Okay. So we said we have zeros at, what did we say? We said we have zeros at 1 and negative, or excuse me, at 0 and negative 1/3. So 0 and negative 1/3. I'm going to have to zoom in and check to make sure those are correct, but they look correct. And then we've got a vertical asymptote right here at x equals 1. What did I write? Sorry. X equals 3. And then we've got 1 right here at x equals negative 3. And then we've got a horizontal asymptote right here at y equals 3. So I'm going to zoom in just to make sure. You know what? My vertical asymptotes don't look right. Maybe I typed this in wrong. Oh, I typed it in wrong again. Sheesh. Get it together, Mr. Fink. Okay, that looks a little better. See, my vertical asymptotes here are definitely at 3 and negative 3. And take my word for it, the zeros are at 0 and negative 1/3. So I'm sorry that took me so long to type in correctly. Okay, so now we're going to learn about holes in graphs, okay? And if you can recall, there were a lot of rational functions that after you simplified them, I would ask you to tell me where x is undefined. And then you would have to take the denominator and set it equal to 0 and figure out what x could not equal. So if we think about that and what the graph actually looks like visually, and we're claiming that x cannot equal a certain value, what does that actually mean? So let me give you an example. Let's say we've got this function here, f of x equals x squared plus 5x plus 6 over x plus 2. And so the first thing you're going to do is simplify that. So this factors to x plus 3 times x plus 2 over x plus 2. And then these x plus 2's cancel out, and we're left with f of x equals x plus 3. And then we go back to our original equation and set our denominator equal to 0, and we figure out that x cannot equal negative 2. So now let's graph this. We've got f of x equals x plus 3, and we know what that looks like. It's just got a slope of 1 and a y-intercept of 3. So I'm going to draw a quick little graph here. 1, 2, 3, 4, 5, 6. So we go up to 3 here, and we go up 1 over 1, up 1 over 1, up 1 over 1, down 1, left 1, down 1, left 1, like so. And our graph looks like this, right? Nice and easy, but x cannot equal negative 2. So at this value right here, at x equals negative 2, what this actually means is that the graph doesn't exist there. There's a hole, Okay? So if I were to draw this more accurately, at this very tiny infinitesimal point in the graph, there's a hole right there. Okay? Let me show you what this looks like on a graphing calculator. So I entered in my original equation, and I'm going to graph that. And we get that nice little graph, just like the one that I drew. Okay? And then what you can do is you can press this button here, second. So second, and then table right here. And let's go to our x values of, whoops, let me look at this real quick. X values, we're interested in the x value of -2 because the graph does not exist there. And you can see that at x equals -2, there's an error. So there's no y value. So it doesn't exist, actually. It doesn't exist. Another way of seeing this is you can hit the zoom button and go to where it says z decimal, hit enter, and it will show you, if you can see, there's a little hole right there at x equals -2. So the way you draw this is just like I did right here. You draw your graph and then you put a little circle where the hole is. And that's what that looks like. So, excuse me. So, this is in the book on page 343, I believe. Yeah, 343, I believe. But it basically says if a rational function has the same factor x minus b in both the numerator and the denominator, just like this one had x plus 2 and x plus 2 in the top and the bottom, then there is a hole in the graph at the point where x equals b. So in our case, x equals -2. Unless, of course, that line x equals b is a vertical asymptote, which sometimes it is an asymptote. But if it's not an asymptote, it's a hole. Okay, a couple of examples here. Wants us to identify the holes in this graph, so we'll go ahead and simplify this by factoring. So we've got x plus 3 times x minus 2 on the top and x minus 2 on the bottom. So which two cancel out, and where do you think the hole is going to be? X minus 2 cancels out, x minus 2 cancels out, and so we've got a graph of x plus 3, and x cannot equal +2. So because we set our denominator equal to 0 and we solve for x, so x cannot equal 2. Then it wants us to graph that. So we're just graphing this simplified version here, f of x equals x plus 3. I think that's the same one that we just did in the example before. So we have a y-intercept here, and just a rise, just a slope of 1. So up 1 over 1, down 1, left 1. And then we have a hole at x equals 2. Right here at x equals 2, I'm going to draw a hole, and then I'll draw my graph through these dots. And that is what our graph looks like. All right. If we started out with x plus 3, it would not have a hole there. But since we started out with this rational function and we simplified it to x plus 3, it's the same thing as x plus 3, except that it has a hole at x equals 2. Okay, and that is it. That is it for 5.4. I will see you in class.